Hello everyone. I decide to solve problems which we calculated and solved in presence class as virtually for your more exercising and concentration, or for more exercise and collecting these problems together as important issues in final exams. Okay, one of the problems we have been solved in presence class was about this power system: a generator called G1, transformer T1, a bus called number 1, a transmission line, another bus number 2, and transformer and generator connected to bus 2 as G2 and T2, and bus number 3 in the middle of power system and transmission lines. And we have two load here: half per unit as active power plus J half per unit and as reactive power. A load is connected to bus 1 per unit plus J half per unit as active and reactive power. Okay, in this power systems we have reactance of generators Gi equal to reactance of transformer equal to reactance of lines is equal to J.2 per unit. Okay, the first inquiry or questions is about finding Y-bus in load flow, used in the load flow. So the first one is find Y-bus in load flow in power system. Please pay attention that we didn't say about the type of transmission line, for example a medium type or short type. So you should consider this transmission line between bus number 1 and number 3 and number 3 to number 2 as a short line without any capacitance. If we have introduced a capacitance, you have to half of capacitance in the beginning and the half of the capacitance admittance in the end of each medium type of transmission line. Okay, for calculating Y-bus used for load flow, we don't consider loads. We don't consider loads, and we consider generator plus transformer as ideal source. So if we have generator and connected transformer, so we use equivalent of ideal source for finding load flow, for finding Y bus in load flow. Please pay attention. So the ideal source and is connected. If this is node number A, this is node number A. Ideal source. Okay. So we model this power system for finding Y bus used in load flow. How we can model? For modeling the power system, we model generation and transformer as an ideal source. Ideal source, bus number 1. We don't consider loads in Y bus in load flow, and the reactance connected between bus number 1 and bus number 3 as J.2 per unit. After that, the reactance J.2 per unit until we reach to bus number 2. After bus number 2, we have an ideal source for modeling generator 2 and transformer number 2. So this is ideal source like these items. Okay, the Y bus used for load flow is a matrix with dimension of 3 in 3 arrays, because we have 3 buses. Okay, let's to calculate each array of Y bus load flow. Y11, each reactances or each connection to connect to bus number 1. This is J.2 as reactance, and it is only connected to the bus number 1. So we should inverse this amount of reactance connected to bus number 1. Okay, inverse of 0.2 per unit, it means 5 minus J5. Minus J5 is also for Y22, but Y33, for considering the bus number 3, the 2 elements is connected to bus number 3. Inverse of J.2 plus J.2, or 2 times of J.2. It means that minus J10 per unit. All of parameters is in per unit. The diagonal arrays of Y bus load flow is calculated. So non-diagonal arrays is y1 2. For non-diagonal array, we have to use minus in our calculation. Minus which element is connected between y between bus number 1 and 2. Bus number 1 and 2, there is no direct element connected between bus number 1 and bus number 2. So this is 0. It is equal to y21. After that, y1 and 3. Between bus number 1 and number 3, we have an element j.2 per unit, and we have to use minus. For non-diagonal array, we use minus in the beginning of calculation of y between 1 and 3. Minus inverse of elements, reactance connected between bus number 1 and bus number 3. It is J5 per unit. This amount of y is equal to y23 is equal to y32 equal to y31. Please pay attention that the y bus we calculated is symmetrical, so the y31 is equal to y13. So in this order we can write y bus load flow is equal to y11 minus j5 per unit, 12 is 0, 13 j5. So because of the y bus is symmetrical, so the first column is equal to first row, 0 j5. y22 is minus j5, j23 is j5, so j5 is here, y33 is minus j10. All of them is in per unit. So we calculate y bus used in load flow. Another question regarding this power system is find y bus used for stability. Y bus for stability needs to redraw your power systems with more attention. In stability analysis, one, we should model loads as y of load, it is equal to S of loads conjugate on V voltage of bus which load connected to it square. The number 2, we model generator in detail to EMF. So if you want to model that power systems, we have to write an EMF of generator 1 as E1 prime. Prime means E prime means EMF of generator in transient mode. Okay, after that we have Jx prime of generator, reactance of generator in transient mode. After that we have J of transformer. After that we have a bus number 1. Between bus number 1 and bus number 3 we have transmission line as J.2 per unit. Between bus number 3 and bus number 2 we have transmission line as J.2 per unit. After that we have a reactance of transformer connected to generator number 2, and after that we have a reactance of generator in transient mode, and after that we have EMF of generator number 2 in transient mode. Another action we have to use in finding or study stability analysis is add extra buses. In front of EMF, in front of reactance of generator, in front of EMF, in front of reactance of generator. So after that we have to rename the buses. The bus number 1 would be here. Bus number 1 in front of, exactly in front of EMF of generator number 1. The bus number 2 in front of bus generator or EMF number 2. After that number 3 in front of reactance of generator number 3, and number 4 is in front of reactance of generator 2, and after that we do the numbering according to the old numbering. After that we have to change number 1 to number 5, number 2 to number 6, and number 7 and number 3 as number 7. So please pay attention that the first renumbering for stability analysis goes to EMF number 1, EMF number 2, the reactance number 1, reactance number 2. After that the changing the number was according to the old name of power system: number 5, number 6, and number 7. This is very important. Okay, the renumbering and adding some buses is finished. After that, we have to calculate the Y bus, to calculate the admittance of loads. We have admittance of load here 1 plus j half per unit. Another load is here half plus half j per unit according to active and reactive powering per unit. And after that, we have to use Y bus of loads and modeling the loads as Y load. The Y load which is connected to bus 5 is S load conjugate over V5, the amount of voltage of bus 5 square. In questions, the question says that consider V5, the amount of voltage 5, equal to V6 to 1 per unit. The main questions gives you this information, and this information comes out from load flow study. The load flow study tell us that the magnitude of voltage number 5 and V6, the magnitude of voltage, is equal to 1 per unit. So we have to calculate load number 5 is equal to 1 plus j half per unit, and its conjugate is minus j half per unit over 1 square. So the Y of load number 5 is equal to 1 minus j half per unit. So Y load number 6 is equal to S conjugate of load over V6 square is half minus j half over 1 square is half minus j half per unit. Okay. So after the finishing the calculation of y of loads in bus number 5 and number 6, we have to calculate Y bus used for stability. The dimension of Y bus used for stability is 7 by 7, and we calculate the Y bus stability in each array. Okay, for Y11 is the minus is the inverse of reactance of generator only connected to bus number 1, and it is J 0.2 per unit, J 0.2 per unit, it is j.2 is equal to minus j 5 per unit. It is equal to y22. After that, we have to calculate y13. 1 between bus number 1 and 3, we have only one element, and so for non-diagonal array we have to use minus inverse of j half. j.2 is j5 per unit. This amount is equal to y35, y57, y76, y64, y42. Please pay attention that the y-bus instability is symmetrical matrix, and for example y35 is equal to y53. After that, we have to use or calculate y33, y33, two elements connected to bus number 3, 2j.2 per unit is connected to bus number 3, and so that it is 2 times of j.2 is minus j10 is equal to y77 equal to y44. But for finding y55, we have a y55, 3 elements is connected to bus number 5, 2 times of 0.2 and a y of load. It is equal to 2 times of j.2 plus y load number 5. That is minus j10 plus y load is 1 minus j5 per unit. It is equal to 1 minus j minus j 10.5 per unit. And so for finding y66, 2 elements of 0.2 is connected to bus number 6. Another element is y load 6 here. So y66 is 2 times of j.2 plus y load of 6 is equal to minus j10 plus half minus j half is equal to half minus j 10.5 per unit. So we draw a Y bus used for stability is Y bus used for stability is equal to the first row is y11 is minus j5 0 j5 and 0 0 0 0. Dimension is 7 and 7, 7 by 7, and after that we have to write 0 j5 0 0 0 0. y22 is minus j5 0 j5 0 0 0 is 0 j5. Another array is 0. y33 is minus j10 0 j5 0 0 0 j5 2 zeros. Minus j10 0 j5 0 0 j5 0 and y55 is written here, y minus j 10.50 10.5 per unit. The y56 is 0, and after that array 5 7 is j5 is j5. Another array is y66. y66 is written here, half minus j 10.5 per unit, and y67 is j5 and y77 is minus j10. This is a pure Y bus stability, which is called as pre-fault. As we remember in the main course and main lesson of stability, we have three regimes in study stability. The first regime is pre-fault. Pre-fault, that is time when we have any fault in power systems. That is, its abbreviation is PRF, pre-fault. So this Y bus stability is called also PRF. After that, fault is started and we feel fault situation. This is during fault. During fault, we are in fault moment. Its abbreviation is DUF. And after that, the fault is cleared, and the time is about the clearing fault, or the fault is not exist. We say that post fault. POF. Many ways we have to introducing or starting post-fault. Maybe the fault is cleared itself. For example, a branch of tree is fall down to power systems and makes the tree phase falls, and after that itself that branch of tree is fall down to the ground, and the fault is cleared automatically without any action, and the fault is cleared itself. Another post fault is the fault is permanent, and the relay, protection relay, and the circuit breaker finds the situation, the faulty situation, and disconnect the lines. So in final questions, you have to pay attention which post fault, which situation of post fault is defined. So after studying of or three regime of stability studying, we introduce reduction matrix reduction. In matrix reduction, we say that our power system Y bus of stability is its rank is very high, and this matrix is very big. So for writing a formula of injected current with Y bus, we have to say that we have some generators. Another buses is non-generator type. So we have here Y bus, stability. After that we have voltage matrix. On which buses is connected to generators, and on that buses are connected to generators, we have EMF. And other buses have regular voltage. So we have I on 0 is equal to A, B, C, D multiple to E prime and regular voltage. So we can use the Y bus and reduction here. The Y bus according to the main course. Please refer to the main course and finding this formula. The Y bus used to stability, but reduction is the bus number R, the bus section R minus B multiple to inverse of D multiple to C, and for matrix here the generator is connected to bus number 1 and 2. So if we want to divide the matrix like ABCD, this submatrix is called A, after that B, after that C, after that D, and we have to calculate R minus B multiple to inverse of D multiple to matrix C. So here I calculate the Y-bus stability reduction as we can see here. Y-bus stability pre-fault and reduction as A minus B the inverse in C. Okay, so you also calculate A minus B the inverse in C with your calculator in MATLAB. MATLAB is a scientific software, maybe in many sites, as we can hear, for finding inverse of matrix, or in applications we introduced in the presence class application in mobile for calculating the inverse of matrix or multiplying matrices. Please pay attention to the notes and do this calculation with your calculator, also in your mobile phone or an online form. So it is very important for final exam. This calculation is obligatory, or you have to do this calculation in final exam. So we introduce all as minus 5j 0 0 minus 5j, and after that we introduce b like this, c like this, also d, and after that inverse of d is here. You can see that the minus of d, the inverse of d here, and you should calculate two numbers after point here, not such exact written here, and after that Y-bus reduction is A minus B inverse of D in C, and after that the Y-bus was written here, Y-bus stability PRF reduction is 0.34 minus J 1.15 0.207 plus 0.59 J, and it is also symmetrical, and after that .22 J 1.11 for as Y-bus in stability and pre-fault reduction. So after calculating Y-bus stability pre-fault situation and reduction, we have to work on during fault and post-fault situation and regime. Please suppose that a question says that a three-phase fault happens in bus tree. The bus tree in the main power system, the bus tree in main power systems is called as a new number of number 7. So we translate a three-phase fault happens in bus tree in main power systems means that fault we have a three-phase fault at bus 7. So and that fault was cleared by opening circuit breaker number 3.1 and circuit breaker number 3.2. Where is these circuit breakers? The circuit breakers is here. The circuit breaker is here. Circuit breaker 3.1 and circuit breaker 3.2. And this circuit breaker is located here. The circuit breaker CB 3.1 and circuit breaker CB 3.2. And so after a three-phase fault happens in bus number 3 or in bus number 7 in renumbering of bus, that fault is cleared by opening the circuit breakers number 32 and 31. So this situation describe the post fault. This situation describe during fault. And the pre-fault, in the situation of pre-fault, nothing happens, and in pre-fault we do the calculations to the end by reduction of pre-fault. Okay, in during fault we have in DUF we have a three-phase fault at bus 7. What happened in Y bus stability during fault? In Y bus stability during fault, we have I1 as a injected current by generator number 1, generator number 2, and after that we don't have any injection of current in each buses. Bus number 3 is 0, 4, 6, 7. 3, 4, 5, 6, and 7. After that we have Y bus with dimension of 7 by 7, and we have E1 prime, E2 prime as EMF of generators. After that, regular voltage of buses V3, V4, V5, V6, and V7. And so, for during fault, as three-phase fault occurs or happens at bus number 7, it means that the voltage of bus number 7 would be 0 because the bus number 7 is connected to the earth. So the bus number 7 voltage, the voltage of bus number 7 would be 0. So the voltage of bus 7 is 0. The I7 is originally 0. So the Y bus, it's not need or not necessary to consider the row number 7 or the column of number 7. So in during fault we can delete row number 7 and column number 7, and we have Y bus stability during fault as dimension of 6 by 6. And after that we can run reduction. Y bus stability during fault reduction, and its dimension is 2 by 2. And so the Y bus stability during fault is minus J5 0 J5 0 0 0. The number 7 is deleted, so 0 J5 0 0 0 minus J5 0 J5 0 0. After that 0 J5 0 0 minus J10 0 J5 0 0 J5 0, and after that Y55 0, excuse me, minus J10, 0, J5, 0, J5, after that Y55, as we calculated before, 0, 0, Y66. The row number 7 and column number 7 is deleted. After that, in reduction, we have to use like this division and finding submatrices. It is A, B prime, C prime, D prime. And so Y bus stability during fault reduction, we have to use R, the submatrix of R equal to B4. So the B is changed, C is changed, D is changed. So we name the B as B prime, C prime, and D prime. Or B new minus B prime, or B new. I decided to rename B and C and D new. New, and new. B new, D minus D inverse new, and C new. You can calculate yourself by your calculator in application form or in MATLAB software, and it is very necessary in final exam to finding A minus B new, D new inverse multiple to C for finding Y bus stability during fault reduction. So, how to use post-fault? In post-fault, POF, in post-fault, the three-phase fault was cleared by opening the circuit breaker 3.1 and circuit breaker 3.2, and it is very important, the connection between bus number 7 and other buses is missed. So if you consider that the bus number 7 is disconnected from power systems, so we lose Y77 as 0, the Y55 changed, the Y66 changed, or we have to recalculate y66 as a new one. The bus number 5 affected, bus number 6 is affected. y57 is equal to y75 would be 0. y76 is equal to y67 would be 0. And so we have to recalculate y bus stability with this consumption. So in this y bus stability pre-fault, we have to some correction in some arrays. So y77 would be 0. y55 is changed. y55 is 2 times of inverse of j.2 is equal to 1 times of j.2 plus 1 per unit. It is y55 new. It is equal to minus j5 plus 1 minus j half. It would be 1 minus j 5.5 per unit. So y55 is changed to 1 minus j 5.5 per unit. The 66 new is y66 new is equal to 1 times j.2 plus y lot 6 is half minus j half is equal to minus j5 plus half minus j half is equal to half minus j 5.5. It would be half minus j 5.5 y57 would be 0. It would be 0. y67 would be 0, and it would be 0. And so that we have to redraw y bus stability as here y bus stability post fault as minus j5 7 0 minus J5, J5, 0, 0, 0, but the row number 7 and the column number 7 which deleted, because all arrays is 0. So 0, J5, 0, 0, J5, 0, 0, 0, J5, 0, 0, 0, 0, and then row number 7 is deleted. Minus J7, 0, J minus J10, 0, J5, 0, 0, J10, 0, J5, J5, 0, 1 minus J5.5, 0, and after that 0, J5, 0, half minus J5.5. This would be Y-bus stability in post-fault. The difference between during fault and post-fault is in during fault we only delete row number 7 and column number 7. In post-fault we first recalculate Y55 new, Y66 new, and we set Y77 as 0, Y57 equal to Y75 as 0, Y76 equal to Y67 as 0. After that, delete row number 7 and column number 7, and so we have post-fault of Y-bus stability. And after that we have to calculate Y-bus stability post-fault and reduction. Its reduction requires the submatrix number A, B, C, and D. But the A is as before, the B is changed, C and D is changed. B is as B new we calculate in the during fault, C also here, but D new is changed. So we can say that A is as pre-fault, B as during fault, as new, C is new, but D I call D2, for example, D2. So A minus B new multiple to D2 inverse multiplying to C new. You can also calculate this Y-bus stability, and its dimension is 2 by 2. Okay. The main goal of finding Y-bus stability reduction for pre-fault, during fault, and post-fault is finding a set of differential equation we need to solve or finding the delta. Delta is the angle of rotor or rotor angle in each situation or regime. Please refer to our main course as we introduced these equations. This equation says that the differential second order of delta I on dt2 is equal to PFS, frequency of system, on inertia of each generator, in the subtract of input mechanical active power of each generator as input minus P output of each generator. The output is electrical and input is mechanical. So in many cases or in ordinary situation, the mechanical input of generator is fixed, for example 1 per unit, but the electrical output power can be determined by the load flow equation, and so we have P output, electrical output of each generation or generator is equal to sigma E I prime EMF prime or EMF of each generator in transient mode multiple to E J prime EMF of other generator. J would be started from 1 to M. For this example, we have one other generator, so M is equal to number 2. So for this example, M is 2. We have 2 generators. So after that, the magnitude of Y I J from reduction multiple to cosinus of the angle of EI prime minus angle of EJ prime as delta J minus angle of YIJ reduction is theta IJ. For example, in pre-fault PRF, in this example, for I for I1 or generator number 1, we have to write P output of generator 1 is equal to sigma j started from 1 to 2 e 1 prime e j prime y 1j reduction of pre-fault prf. So if I want to write it clearly, pre-fault prf reduction, okay, and so that the cosinus of delta 1 minus delta j minus theta 1j. Okay, after that we can extract as e1 prime e1 prime y11 prf reduction cosinus delta 1 minus delta 1 minus theta 1 plus e1 prime e2 prime y12 prf reduction cosinus of delta 1 minus delta 2 minus theta 12. Okay, after that we can use y-bus reduction as y-bus yes yes so we have we have y-bus stability pre-fault reduction here, and it is 0.34 minus j 1.15, and we have to calculate this number as magnitude, and it is 1.2 with the angle of minus 73 minus 33.5 y21 is equal to, we calculate by calculator, plus I is equal to 0.62 with angle of 70.6, and for this number is 113 with angle of minus 78.8. So the y11 is the magnitude. Its magnitude is equal to 1.2. Delta 1 and delta 1 is deleted together. Theta 11 is the theta 11 is minus 73.5, and the angle of theta 1 2 is 70.6. Delta 1 is minus 73.5. The delta 2 is minus 78.8. After that, the magnitude of y12 is 62, and after that, for finding P outputs in generator 1, we have to calculate E1 prime and E2 prime. E1 prime as E2 prime were remained, and we have to calculate. In our course, for finding E1, please refer to the examples we described in the main course, and for calculating E1 prime, for finding E prime of each generator, we have to use a KVL equation for this highlighted region. E1 prime is equal to V1 as a terminal voltage plus JXD1 prime in I1. So V1, V2, V3 as a voltage, terminal voltage of each generator, for example bus number 1, bus number 3, bus number 2, is find from running load flow. For that situation, in the main question, we give you the result of power flow as this column. The magnitude of voltage in each buses is achieved from running load flow, and it is input of each question for solving stability. And after that, you have to substitute the voltage as power flow result here. XD prime is obviously or clear in as an input of question, but the I1 is required. The I1 comes from this equation. What is this equation? According to the main course we taught before, I1 or the current or injected current of each generator based buses, for example I1, I2, I3, these three buses is generation based buses, and its result is here. the generator active power is here, reactive power is here. Active power and reactive power generated for 3 buses is here. Is S of generation conjugate on voltage of each buses we want to calculate. For example, this is I1, the V is 1, conjugate. For example, 1.052 minus 1.073 is here, and V1 conjugate is 1.06 with the angle of 0. Conjugate is in here, and I1 is calculated. So we have to use E1 for this example as here. E1 E prime 1 is equal to, as we used in the main course, is V1 plus JXD1 prime I1. And I1 is calculated as S generation conjugate over V1 conjugate. E2 is equal to V2 plus JX D2 prime I2, and I2 is S generation conjugate of generator number 2 V2 conjugate. So suppose that we have as an input of the questions that SLB bus, the bus number 1. The bus number 1 has active and reactive power as, for example, 1.1 1.2 plus J.7 as active generation and reactive generation, with the voltage of the magnitude of voltage is 1.08 with the angle of 0, and PV bus, the bus number 2, is 0.3 J.3 per unit with the angle of 1.05 with the angle of 1.5 degree. So In for finding I1, we have to conjugate the generation of generator number 1, 1.2 minus j 0.7 over V1 conjugate. V1 conjugate is 1.08. And after that, I2 is conjugate of generation power of generator number 2 minus j 0.3 over 1.04 minus 1.5. Remember that the conjugate can change the sign of angle. So E of prime 1 is V1 is 1.8 with the angle of 0 plus j 2.2 per unit, as we say that in this part. And after that, multiple to I1, 1.2 minus j 0.7 over 1 108, and E2 prime is 1.04 with the angle of 1.5 plus j 0.2. In I2 is 0.3 minus 0.3 j over 1.04 minus 1.5. I want to find the final value of E1 prime and E2 prime. Please calculate these equations with your own calculator yourself. It is very important for final exam. It is 1.22 with the angle of 10.4 per unit. E2 prime is 0.084 with the angle of 48 degree per unit. So according to the main course, after finding E1 prime and E2 prime, we have to recalculate PO1 and PO2. The PO1 is PO, the output, electrical output power of generator number 1 is E1 prime multiple to E1 prime. So it is E1 prime in this equation is a magnitude 1.22 square multiple to 1.2, 1.2, and cosinus of minus 73.5 plus E1 prime is 1.22 in 0.084 multiple to 0.62 cosinus of this equation minus 73.5 minus 78.8 and 70.6. This would be minus 65.3. So the output is is 53.533, and so the active output, electrical output power of generator 1 is determined per unit. So you can write as and substitute the value in the main equation. D2 delta 1 dt2 is equal to P in 50 Hertz on HI, P input of generator 1, this is inertia of generator 1, minus 0.533 per unit. Maybe the questions gives you the inertia, maybe holding in parametric. So after that, you can write this equation as a differential location in second order with d delta 1 on dt is omega 1. This set is for generator 1 for G1 in pre-fault situation, and after solving these equations with many methods, you can find delta 1 t. After that, this is for pre-fault situation and for generator number 1. After that, for generator number 2 and pre-fault situation, you have to do this procedure as we say or write before. D2 delta 2 over dt2 is P in 50 Hertz on H2, P mechanical input of 2 minus P output, electrical active power output of generator number 2, and d delta 2 over dt is omega 2. The PO2 can be calculated in disparate procedures like this. And after that, after substitute the PO2, you can write delta 2 T. Delta 1 and delta 2 is determined after solving this differential equation, and you can demonstrate or draw delta 1 and delta 2 as a pre-fault. After that, you can write these two sets for during fault. For example, G1 during fault is D2 delta 2 dt2 is 50 pi on H1, excuse me, delta 1 d2 delta 1 on dt2, 50 pi on H1, P mechanical input of generator 1 minus P output of 1, and d delta 1 dt is omega 1. The PO1 in during fault, you have to do it in during fault. PO1 is sigma E1 J equal to 1 or 2 mine E1 prime EJ prime Y1J magnitude cosinus of delta 1 minus delta J minus theta IJ. The Yij comes from Y bus stability during fault and reduction. The E1 and EJ is determined as before. And after that, for during fault, for generator 2 and during fault, we have to write a set of differential equation. D delta 2 dt2 is equal to 50 pi H2 P input of generator 2 minus P output of generator 2 d delta 2 over dt is omega 2. And after solving this equation, the differential equation, you can get delta 2 during fault change by time, and this is delta 1 during fault T. This delta is for pre-fault PRF, and this is PRF. So you can depict the drawing of delta 1 and delta 2 in during fault. After that, we started G1 in post fault. d delta 1 d2 dt2 is 50 pi, excuse me, 50 pi h1 p mechanical input of generator 1 minus po1 d delta 1 on dt is omega 1. This gives you delta 1 in POF over T. PO1 in post-fault is equal to sigma j equal to 1, 2, 2, E 1 prime, EJ prime, Yij magnitude cosinus of delta 1 minus delta j minus theta I theta 1j, and you have to use Y bus stability post-fault reduction for the magnitude of Y1j. E1 prime, EJ prime are as before, but the Yij comes from Y bus stability post-fault reduction. Also, the set of differential equation in second order can be right for generator number 2, d delta 2 over dt2 is 50 pi h2 p input 2 minus p output 2, and d delta 2 over dt is omega 2, and after solving this set we can get delta 1 delta 2 post fault change for in time domain, depicted in time domain. So after that we have 6 delta. If you suppose that the t is equal to 0, it is a start of during fault, and fault is continue or goes on to TC. TC is clearing time. This is the period of time of DUF. After that we have POF. The before DUF we have PRF. So for 2 generator we have delta 1 PRF and delta 2 PRF. After that during fault we have delta 1 during fault and delta 2 during fault. Post fault is delta 1 POF and delta 2 POF. We have 6 delta, 3, 4 delta 1 and 3, 4 delta 2. The delta 1 and delta 2 is very important, but delta 1 minus delta 2 is so important. That is called delta 1, 2 in PRF. It shows that the synchronism between the generator number 1 and 2, delta 1, 2 in DOF is important, and delta 1, 2 POF is important also. In final exams we only expect to solve like this example. We don't need to find the final value of delta 1 in pre-fault, during fault, post-fault, but we need to solve this set of differential equations, and we need to uh, calculate and write this uh, calculation. Also, we have in main course, we try to solve an example in the main course, and the full detail is uh, bring it out for you for finding how another examples can be calculated. And after that, we can depict the during fault, pre-fault, post-fault set of differential equations here. And after that, after solving this set of differential equation, we can be depict or draw the delta, for example, delta 2 1, delta 2 1 and delta 3 1 as the synchronous between generator 1 with 2 and generator 3 with 1, and you can see that this oscillation. After that, in unstable situation, this differential between two angle of two generator in this picture, you can see that delta 3 1 has a synchronism, but the delta 2 1 is not stable and goes to infinite, but the delta 3 1 is stable, or oscillation is amplitude of oscillation is limited. So I think that this is almost the complete example we could determine as another example after the main course example about the stability. Thank you very much.